All right, guys, hello again and welcome to G Squared Academy, where you know excellence is indeed epitomized. So, what we're going to be looking at today is the reason why transition metals are colored. Now, transition metals is a part of the CAPE syllabus, is a part of IB chemistry. Now, here's the first thing that we need to remember. We need to remember that transition metals, and we're looking at first order transition metals really right now. Transition metals, there are 5D orbitals. They are D block elements. So there are 5D orbitals. One, two, three, four, five. There are 5D orbitals, right? And when the transition metal is not involved in bonding, these 5D orbitals are what we call degenerate. Or in other words, they have the same energy. Okay, they have the same energy. When, however, um the transition metal is bonded to something, right, bonded to a ligand as we call it, then what happens is that that ligand splits the d orbitals, and it splits it in one of two ways. Either it can split it where you have two at the top there and three at the bottom, or you can have three at the top and two at the bottom. Okay, there are differences in structure with respect to these things, right? And there are symmetries or shapes, symmetries really, that produce this sort of splitting versus this sort of splitting. We're not getting into the names of the type of split, we're just looking at why transition metals are colored. So something like iron 3, for example, Fe3 plus, right? Now remember that for Fe3 plus, you're going to lose the 4s 2 electrons first, and then since it would be D6, it loses one of that, so it becomes D5. So Fe3 plus is D5. Okay, so we can organize those electrons like this: 1, 2, 3, 4, 5, right? Now, what happens is that when you irradiate a sample with iron, for example, or when you are allowed, you give it energy, really, one of these electrons down here can jump up here. It gains a photon of energy that allows it to jump up here to this set of d orbitals. Okay, it can't stay there forever because that's just how these samples are. And so, therefore, what will happen is that it will lose that energy and fall back down, emitting a photon of energy, right? Now, this is absorption. We're going to put as abs, and this is emission. Okay, so that's emission. Now, what tends to happen for transition metal complexes is that the energy emitted here from this gap up here to down here, the energy emitted corresponds to a wavelength of light which is in the visible region of the electromagnetic spectrum. Okay, so this wavelength of light which is emitted um produces a color on the electromagnetic spectrum. Now, that's pretty much why these transition metals are colored. Now, one of the things we don't tend to look at really is the fact that we have unpaired electrons. If all the electrons are paired up, then there's no way for any electron to jump up to another orbital because there's no space for it to go. Okay, so in a situation where we have D10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In a situation where you have D10, this will not be colored. And of course, this will also not be magnetic. And we'll do a video about magnetism as well. But it will not be colored because there is nowhere for these electrons down here to jump up. There's no space for them to go. So therefore, then when they absorb energy, right, the energy is not going to produce a jumping up for the electron or an excitation of the electron and then releasing or emission of energy, which produces a color on the electromagnetic spectrum. So when we have free or unpaired electrons, those electrons can absorb energy, jump up to one of these d orbitals, and then fall back down, emitting a wavelength of light which corresponds to a section of the electromagnetic spectrum which we can see, or the visible region of the spectrum. So I hope this helps you guys to understand why transition metals are colored, and I wish you all the best. We'll meet next time.